In this video, we're going to be talking about the Lagrangian. The Lagrangian is defined as the kinetic energy minus the potential energy. If I were to write this out, I end up with 1/2 mv squared minus u. The Lagrangian is a functional, and it is a functional of position, velocity, and time. Position and velocity might both depend on time. Let's look at the two halves of the Euler-Lagrange equation. Here we're just considering the x direction. dl by dx, I have no terms in the kinetic energy that depend directly on x, but I end up with minus du by dx. That's the force in the x direction. Likewise, if I look at dl by dx dot, I have terms that depend on the different components of the velocity in my kinetic energy, but none in my potential energy. So that tells me that the derivative of this is going to be mx dot, and that's the momentum in the x direction. What my Euler-Lagrange equations tell me is that the force in the x direction is equal to the rate of change of my momentum in the x direction. Or more generally, force is equal to dp by dt. This is exactly Newton's equations, but done in a slightly different format. All of these Euler-Lagrange equations are going to be second-order differential equations for each of the coordinates in my system. Hamilton's principle is something that governs this type of Lagrangian mechanics. The action is defined as the integral from some time t1 to a later time t2 of the Lagrangian dt. Hamilton's principle says that path a particle takes is the one for which the action is stationary. Imagine I have my coordinates t1 and t2 in this system, and I have many places for the particle to go. The one that is going to give me the dynamics is the one for which the action is stationary. The action is the integral of the Lagrangian, so therefore the Euler-Lagrange equations guarantee that this system will have stationary action, and therefore these are the dynamics of the system. Generalized coordinates are something that make the Lagrangian method so much more powerful than just solving force is equal to dp by dt. Imagine that we have some change in coordinates. So my original coordinates are the Cartesian coordinates, ri, x, y, and z, and I've got some new set of coordinates, qi, here, which are functions of x, y, and z. And I'm going to have 3 of them. This could be like changing to spherical coordinates. But the point here is that these can be any type of coordinates you'd like. My initial Lagrangian in terms of my Cartesian coordinates is going to be 1/2 mv squared minus u of r. And this is equal to my Lagrangian in these new coordinates. So I've got q1, q2, and q3, and q1 dot, q2 dot, and q3 dot, and these are all a function of time. What Hamilton's principle says is the action for my system, whether it is based on the Lagrangian expressed in terms of Cartesian coordinates or expressed in terms of these what are called generalized coordinates, is going to be the same. This action is the same as the action in Cartesian coordinates, so that means that the dynamics will satisfy the same equations in the new coordinate system. They have to satisfy the Euler-Lagrange equations. That tells me that dl by dqi is equal to d by dt of dl by dqi dot for all I. There's a little caveat here that the QIs have to be an inertial coordinate system, so a coordinate system that does not depend on time, for the physics interpretation of this to make sense. And in this set of coordinates, we have what are called generalized force. So dl by dqi gives us a generalized force and dl by dqi dot is what's called the generalized momentum. So these may not have a strict physical interpretation the same as force and momentum in Cartesian coordinates are concerned, but these quantities are extremely useful in calculating different types of dynamics. Let's have a look at Lagrange's equations for a free particle. So we've got some particle here and it's traveling with velocity v. In Cartesian coordinates, we'd write this as 1/2 m x dot squared plus y dot squared minus the potential energy as a function of x and y. If I were to write down the Euler-Lagrange equations for this, I get two. I get one for x and one for y. These are going to give me force in the x direction is minus the derivative of the potential in the x direction. Because these are symmetric, I get exactly the same thing for y. What about polar coordinates? So this is an example of one of these changes in coordinates. The first thing I want to do is express my velocity in terms of these coordinates. Here I've got v is equal to r dot in the r direction and r times theta dot in the theta direction. And now I can look at 1/2 mv squared from this definition and re-express my Lagrangian in terms of these new coordinates. This is 1/2 m times r dot squared plus r squared theta dot squared minus the potential as a function of r and theta. So just a reminder about how these gradient operators work in polar coordinates. Force is equal to minus the gradient of u. This is minus du by dr in the r hat direction minus 1/r du by d theta in the theta hat direction. Let's look at the Euler-Lagrange equation for r. dl by dr is equal to d by dt of dl by dr dot. dl by dr has a term coming from the kinetic energy, unlike in the Cartesian case. So we end up with mr theta dot squared minus du by dr, so our standard derivative of the potential, and that's equal to mr double dot. What is this telling us? This is telling us that the centripetal acceleration, or r omega squared, minus the force from the potential is equal to the total force in the r direction. And the Euler-Lagrange equation for theta, dl by d theta is equal to d by dt, dl by d theta dot. We have minus the derivative of u with respect to theta is equal to d by dt of mr squared theta dot. You'll notice this term here is equal to the force in the theta hat direction times r. So that's a torque, and this is equal to d by dt of mr squared theta dot, and this is our angular momentum. Just from the Euler-Lagrange equations, we get that torque is equal to the rate of change of angular momentum. Equivalently, this is equal to I times the angular acceleration. For generalized coordinates, the thing about them that's really great is that you can pick any coordinates you want, and these can be designed to make your problem easier. Usually what you do is you write down the x and y components of these coordinates and use those to get the velocity in your system, and then you can use that to find your kinetic energy. So you write down your kinetic energy in terms of your generalized coordinates and your potential energy in terms of those generalized coordinates, and then just use these Euler-Lagrange equations to solve. Let's take a look at a couple of special cases that will make your integration for these systems a lot easier. Here's our Lagrangian, the kinetic energy minus the potential energy, and our Euler-Lagrange equation in terms of our generalized coordinates, Q. This term on the left, these are my generalized forces, and the terms on the right are the rate of change of my generalized momentum. This is going to be the equation for the dynamics of my system, regardless of what my q's are. So typically what you do is you choose q, then you write down the components of q in Cartesian coordinates so you can easily figure out what the velocity is in terms of your new q's. And then you write down your kinetic energy in terms of these q dots and your potential energy in terms of your q's. Then this Euler-Lagrange equation solves the dynamics no matter what. Here are a couple of special cases that'll save you some time when you're integrating different systems. Imagine that the Lagrangian does not depend explicitly on qi. That tells me that this first term here, dl by dqi, is equal to 0. d by dt of dl by dqi dot is equal to 0. Or dl by dqi is a constant. Another special case is when L does not depend explicitly on time. This is a pretty standard special case. I have dl by dt. The total derivative of the Lagrangian with respect to time is equal to partial derivative of the Lagrangian with respect to time plus dqi by dt times dl by dqi plus dqi dot by dt dl by dqi. And we know that from the definition, partial L by partial t is equal to 0, since the Lagrangian does not depend on time. This term over here, just by the definition of the Euler-Lagrange equation, is equal to d by dt of dl by dqi dot. That lets us rewrite both of these terms using the chain rule to say that the whole right side of our equation is equal to d by dt of qi dot dl by dqi dot. And that's equal to the total derivative of the Lagrangian with respect to time. I can write this as d by dt of L minus qi dot dl by dqi dot is equal to 0, or equivalently, L minus qi dot times dl by dqi is equal to a constant. That would be integrating the second order Euler-Lagrange equation to a first order differential equation. And we've spent a lot of time thinking about many ways we might solve this. That can help you the dynamics for specific cases.